Hi, this is Corey. I'm just making a quick demo of the operation of our FPGA with the Mario Kart game. And right now what we have is mostly a proof of concept at the moment. So these are our 4 buttons, up, down, left, right. We got a bit more work on this to do, but after a long night of ironing out bugs and problems with our project, we got something that will interact with the user. So Mario will go left, will go right, and he'll go up and down whenever you hit the corresponding button. Hi, this is Corey. I'd like to talk about the accelerometer that we had planned for our FPGA, our CPU. It uses the I2C protocol to communicate with the FPGA board. There's a couple of procedures. There's a write procedure and a read procedure that's a little bit more complicated. And then you implement I2C basically by writing a state machine, and you want your waveforms to look like so. You first send a start sequence, then you send 7 address bits, and then a read-write bit that tells the device whether you're going to read to it or write to it, and you wait for that device to send back an acknowledge bit. Then you send or receive 8 data bits. And there's also the ability with I2C to send a repeated start. So if I wanted to read from a device, I would first send the address for the device, and then I would write the register that I want to receive data from. The accelerometer has several registers that you can read data from. It has the x-axis, the y-axis, and the z-axis, both high and low bits, or high and low bytes, and a gyroscope, and there's a lot of other data. It even has a temperature sensor. And then after writing that register that you want to receive the data from, you send a repeated start condition, and then you send the address again with a read bit, and then it sends you the data. So I just want to go over how I've attempted to implement this. This file right here is my first attempt at a state machine. You can see the different states, the acknowledge state, as an acknowledged state right here, send data, stop state, start state. And it was after writing this that I figured out that the read procedure required a repeated start, and it was a little bit more complicated than this design was allowing me to do. And so I started on this design right here. This has a few more states, and it's a little more complex. But the one thing I found out with this design is I wasn't getting the clock pulsing right. And so, as kind of a last resort, I went to Busmaster version 3. Let's see if I can find it really quick. So, Busmaster v3 was more of a hard-coded attempt to just, it was kind of a painstakingly attempt to assign the clock and the data line at every single state instead of using counters. This one, for the most part, has worked better than the other two. The only problem is I haven't quite gotten this to sync up with the FSM for the control and the ready signals. This FSM tells the I2C Busmaster which data to read and write from, or which registers to write to or to read from. And so I haven't gotten this all figured out and bug-free and squared away yet in order to get input from the accelerometer, but I was able to check the data sheet on the accelerometer, and I was able to use the I2C protocol successfully on an Arduino. It's just not working on the FPGA quite yet. So what I did for our CPU is I augmented it with buttons. For our Super Mario game, we've got an up button, a down button, left button, and a right button. And the left and right buttons simulate 2's complement, sine 2's complement data as that's how it would come from the accelerometer register. So if you hit the left button, it gives a 2's complement minimum. If you hit the right button, it gives the 2's complement maximum to the accelerator input, or accelerometer input. The other thing I had to add was some instructions. Store the up and down, and then store left and right. And what it does is it just uses a mux to take the data from the button inputs, and it puts the up and down values into register 14, and it puts the left and right values into register 15. Thank you very much.
Hi, my name is Jason. Like Corey just demonstrated, he kind of went over a couple of the instruction set and a little bit of the code behind our software and kind of backing for the CPU that we use for the project. I'll go over a couple of kind of our design for the actual CPU of the of this project, as well as a little bit of how we started to ease our way into developing the software for it. So here we made this table for just ease of access in terms of writing our instruction set. It's very simple. It's pretty much exactly how the ISA document is outlined, with the ordering of the destination registers, the source registers, and the way that they're structured. The actual opcode is structured. So we mapped it all out just so we can easily determine what we had to write in terms of assembly and for the software. And all of these instructions cover the basis of what we need, including the adds, the subtracts, the compares, which are a big part in terms for the game logic, and then just logical operators such as ands, ors, xors, shifts, and some of the more important ones were load and store, as well as the branching instructions and the jumps. And Corey went over the custom instructions that we made specifically for the receiving input from our accelerometer and input buttons. So those are just some custom instructions that we designed specifically for our CPU. But one thing to note, that for our branch and our jump instructions, most of them we consider to be pseudo instructions. So they're technically just two instructions that we combine into one. Like for most of the branching and for the jumps that deal with conditions, we do the compare instruction first, and then do the actual branch or jump command immediately following it. But for ease of writing, for ease of just looking at in terms of code, we just combined them into one instruction, just for making writing our code a lot easier. And the way we wrote our code, we had the help of a custom assembler that I built in Python. And here is most of the structure for it. So for some of the pseudo instructions that dealt with more specific cases, such as dealing with two commands, the compare and the branch, or the compare and the jump, they had to be split into two parts, whereas the rest of the information could just be held with their opcodes directly. And then I just performed the logic depending on whether or not it was a pseudo instruction or just a regular opcode, to help split it up into the necessary parts and order it in the way that it's supposed to be. And by that I mean just making sure that the structure matches where the first part of the opcode is and where the destination register is, and all that just for ease of use in terms of putting it in the right order where it needs to be. And of course, just for ease of writing this, it takes in just an example file for reference, structured similar to this, where we'd write it in English and just in assembly with instructions right out, and it would output the hex file so that we can give it directly to our memory. And kind of following along that same logic, the actual structure of our CPU, here's the block diagram for it. We have our VRAM, our memory, where it reads in our opcodes and our data file, which holds the information of where like our glyphs are, right when they start out, as well as a place for us to write to, so that our address generator can read from those locations. We have our main FSM that gets passed all that information from the VRAM to determine what type of action needs to happen. For example, we handle all of our jumps and our branching instructions from here, which then pass on to the data path, which is this big block on the right. A couple things to note, though, in terms of our specific design that differ a little bit from this, is that we determined whether or not it was an R-type or an I-type instruction in the data path itself rather than in the FSM, as well as dealing with an immediate directly, instead of having a mux to determine if it was an immediate. It was, we just tagged it along with at the very beginning part of the data path. Other parts to remember, to note, when dealing with our program counter, which is this upper left-hand side of the block diagram, we did implement a mux to basically a jump enable, which allows us to essentially jump to where in memory we needed to be inside of the VRAM, or inside of memory essentially, but only when that jump enable was high or on. So this is kind of the structure and the way we designed our CPU, as well as the kind of the backing behind the building of the software. And yeah, so there's our structure.
Okay, I'm Todd Nielsen, and I'm going to go over our instructions. So to control the Mario guy, so from here to here, it's the initial setup. So we load the X location from memory into register 0, and this location is related to right here. We read it in with an offset of 80, just so we knew where it was. And this is the Y position of the Mario. This is the Y position of the obstacle. And then we, this is a counter limit that's used to, as kind of to slow down the Mario so that we could see him because he was going too fast. Then we load the Mario X and Y position. And then right here is, this value signifies if the up button is being pushed, which causes Mario to go up the screen. This is the down button, which causes them to go down, and these are the right and left values. And right here is the beginning of our game loop. And right here, if the up button is not pushed, then we skip this, and it goes down to down here. And this is if the down button is not pushed, we skip that. If the right button is not pushed, then we skip that. And if the left button is not pushed, then we skip that. And then these final two, simply there's the obstacle going across the screen, storing that position, and this just slows down the clock by about 16,000 instructions so that we can have better control of the Mario. I also worked with Yi on this. This is our address generator. So I created the glyph of the Mario guy and the obstacle. And so these are the colors of our background. And what it does is it goes through, the size of the Mario is 32 by 32, which is a 1024. Same thing with our obstacle. And so it fetches the X position, and then the Y position, and then enables the move. Same thing with the X and Y position of the obstacle. And then we display it on the screen. And we store those in our glyph ROM when we have offsets. So right here, we have the offset for the obstacle, and we read in the Mario, and then we display it in the address generator. Thanks.
Hi, my name is E, and my part for our Mario Kart is the VJ display. So firstly, I just found some pixels for the obstacle like a turtle, and another one is the Mario Kart, the backboard of the Mario Kart. And after that, I use this website to get rid of the background color of the picture I get from the website to just get a pixel which can be used in our code. And this website can export the .c file. So we can use the code our tier Chris gave to us to maybe include different .h file and convert to different .hex file to be read into our Verilog. And here's our obstacle and the Mario Kart file. So firstly, we tried with maybe 11 same glyphs to move like without our input. But after that, we just read one glyph and just remove that glyph inside with our input files, without input values. And here's our hex files. And also for our display part, we would like to have some fancy root in the background, but actually when I try to have this file inside our code, this file is too big, and we cannot just read them in our code because it will run out of our memories. So we cannot maybe move our Mario Kart. So that's why we choose to just do some hard code part in our BigGen, because this is for how to display our read files and backgrounds. And firstly, we have a pix enable to check if we have a pixel need to display in our screen. And otherwise, we just need to display for the game background. And for our background we want a check in the middle of our screen, and also there are two bounds on the left and the right of our check, and otherwise there are the background color. So I choose the background color to light green and the check color to gray and the bound color to white, which is easy to be tell the difference from the MarioKart and obstacle with the background. In this way, we can just read our hex files, and firstly, we can just read the MarioKart hex file from the 0 address in the row. And but for the second one, we need to start at the 10,010 which is 32 times 32, because our glyph file is 32 bits times 32 bits. That's why we choose 2 bits. That's all for my part. Thanks.